Okay, so hello everybody, and thank you for having me. So now we are going to talk about the animated stickers feature in Telegram and the remote attack surface it exposes. This is going to be our agenda. So first, as always, a little introduction about who I am and what is the Lottie animation format. Then we'll switch to the Samsung R Lottie project and its integration in Telegram. Then we'll move to the actual technical part, which is my fuzzing efforts and the issues I have identified in Telegram. And last but not least, some closing remarks and conclusions. So before I begin, I just want to ask you if anybody in this room is part of this Telegram group. You can raise your hand. OK, quite some of you. OK. So since we are going to talk about Telegram vulnerabilities, remember that we are actually watching you. So I would suggest you to disable your internet connection during the talk and after. Of course, I'm joking. So let's dive into the introduction. So as I said, I'm Polict. I'm a vulnerability researcher and exploit developer at Shielder. Currently, I'm also the research team director there. In my free time, I enjoy backpacking around the world. And you can ping me on Twitter in case you don't get the chance to ask a question to me. And please note that all opinions expressed in this talk are mine. So what is the Lottie animation format? Basically, it's an image format based on vector graphics created by Airbnb. And you can create a Lottie animation by directly translating Adobe After Effects. On the right part of the screen, you can actually see an example of a Lottie animation. This comes from a Galaxy Watch app by Samsung. And you can see here a small list of the vendors actually using Lottie animations. Most probably, the most important here for us is Signal, but remember that most of the vendors actually render animations coming from the local file system, so they are not remote images. So technically, what is a Lottie animation? Basically, it's a JSON-based text. You can see here the 5 main attributes it needs. So first, there is the version identifier, then the frame rate, in-point, out-point, and last but not least, the layers attribute, which is actually the most interesting one because it contains the actual vector graphics animations and changes in the animation. So let's move to Samsung R Lottie project and its integration in Telegram. So basically, the R Lottie project is a C++ library for rendering Lottie animations, and it is more performant than the Airbnb's Swift or Java libraries. As I said, it's developed by Samsung and it's open source. You can surf its code on GitHub. But there is a twist, because they don't actually track security bugs coming from parsing untrusted images, remote untrusted images. This is, of course, a legit decision by them. But in case of Telegram, this creates a problem because they will need to track and fix all of the issues coming from parsing animated stickers in Telegram themselves. So let's have a look at the main APIs in R Lottie and how we can use it to actually render an animation. So first, there is the import function, which is the load from file method, which will load the JSON from the file system. Then we can directly render a specific frame number in a surface buffer. So basically, we have everything we need in order to create our harness and start fuzzing this. So how it's rlotty integrated in Telegram. Basically, first, the animated sticker is sent, and this is the general flow of an animated sticker and where it starts and where it ends its journey. It starts from being sent from a client, and note here that you don't actually need a real device in order to start a Telegram chat. You can just emulate a device. After it is sent, it is received by the victim, and depending on the client, the animated sticker is parsed and rendered either when you open the chat or just when the victim receives the sticker. So this makes the difference between a 0 or 1-click remote attack. Once the animated sticker is rendered, it actually, depending on the client, for example, we are going to see the Android code for Telegram, and in that case, the Java code will call the rlotty native library through the Java native interface. In the end, rlotty will decode and parse the animation as we have just seen in the quick start. So let's dive into the Telegram code for Android. As you can see, first, once the client receives an image in a chat, it checks the MIME type of the image. In this case, application/x tg sticker is the MIME type corresponding to the animated stickers. And you can see that in that case, it sets the image type to image type lotty, since it's going to be animation and it's going to be rendered. Then it creates the rlotty drivable object, which will in turn call the actual rlotty API we have seen in the quick start and we can use in order to fuzz it. So as we have seen, basically, rlotty is reachable remotely, and it may make a difference between a 0 or 1-click attack, but it is actually C++ code reachable remotely, so it's a problem. Another thing to note is that by default, the Telegram official clients enable all the animations in the chat. So by default, you get any animated stickers you receive rendered on your phone by default. So let's move to my fuzzing efforts. I have a kind of North Star here, since also like Magnus mentioned this morning, I also try to do like the easiest way possible first, then maybe move on and get smarter. Here is the same, so I will try to fuzz it in the easiest way for me possible, and then if I see that there is actually the possibility to be smarter and find some more issues, I will try that. You can see this meme represents basically this concept, and this comes from InfoSec. So what we can do, what is the easiest way in order to fuzz this, in order to fuzz rlotty? As we have seen, it's an open source project, so you can basically instrument it and fuzz it how you want. Personally, I've started by using AFL++, but of course, you can use any fuzzer you prefer, so libfuzzer, ongfuzzer, or whatever you prefer. I think 3 are the main things to note here. The first is that the corpus, so the starting files from which mutate and create new potentially crashing test cases can be extracted from actual community-generated animated stickers, because when I tested this, the animated sticker feature was actually just released, so a lot of people already started generating animated stickers just to try it, and also because, as I mentioned, the animated stickers are actually smaller in size than GIFs and videos, so they are more easily shared in the chat. The second thing to note here is that the crashes actually started to appear after just some seconds, so either no one fuzzed this or who fuzzed this didn't report the vulnerabilities to either Telegram or Samsung themselves. I think the latter. Third point about minimization, we are going to talk about this also later, is an endless brute force because as we have seen, since the animated stickers are actually JSON-based text, a minimizer will just try to remove some bytes, but will most probably break the JSON syntax, so it's useless and it's just a brute force cycle. A thing to note here is that not only minimization is going to be a brute force, but also the root cause analysis will be hard since you don't know actually which part of the animation is crashing the library. So for who has done already some fuzzing, you can recognize this view. This is actually the AFL WhatsApp view. You can see here, this comes actually from the very first fuzzing cycle I did. You can see the hardware specs below. And in this view, you can see that after just 13 days, it has found 1,500 crashes. Again, here, AFL is not that smart because it can't differentiate between two crashes which are actually the same, but the animation is different because it might be a different code path. So after doing this, I wondered, okay, there are a lot of bugs here. Let's see how I can make this in a smarter way. So I can avoid brute forcing the minimization or avoid spending so much CPU cycles in order to mutate a JSON and most probably create a bad JSON because it doesn't respect the JSON syntax. Google has created this technology called protocol buffers, which are basically C++ structures, but in a language agnostic way. So you have the message, which is almost the struct keyword, and then the name of the message. By using this technology, you can pretty much describe anything. In this case, you can see a simple example of a person with three attributes, the name, the identifier, and the email. And by using protocol buffers, you can just encode and decode information by respecting this specification. Anyway, you can read more at the link below. So we know that Lottie has actually a specification. rLottie, the Samsung library, is a little bit different, so I created the grammar for this library in specific since I wanted to pawn Telegram. And as you can see in this preview, there are two custom messages, which are the layers attribute and the assets attribute. The other are pretty much basic ones. Writing the grammar for the rLottie protocol was pretty hard since it wasn't done before, so I couldn't start from something already done. I had to write it from scratch. And I had to decide between the protobuf version 2 or version 3. In the end, I chose version 2 because they allowed the optional statements, but it was hard in the end. So, by writing a protobuf grammar, we can actually use a custom mutator in any fuzzer we want. In this case, Google has also created this libprotobuf mutator, which is a custom mutator which can actually mutate protocol protobufs. So in this case, I'm not going to use anymore the built-in libfuzzer mutator, but I will move to that. So how is the structured fuzzing flow like in a high view? Basically, by starting from the grammar, we can ask the mutator to mutate a randomly generated animated sticker, which will arrive at the harness because you must note that since protobufs are not actually JSONs, we need a way in order to translate this protobuf view into a JSON, because our library actually parses JSONs. So in the harness, I wrote the code in order to do this translation, which will in turn go to libfuzzer and test that specific test case with the libfuzzer instrumentation, and will collect the coverage in order to potentially mutate the new animated stickers in a different way in order to reach more coverage. So let's have a little comparison of the fuzzers I wrote. Of course, here it's just my experience. Your mileage may vary, since this was a really specific project which might not be compatible with other things. So I've divided basically my fuzzers into two types. The first is the standard coverage guided, so just instrumentation, then running with a simple starting corpus, and then structure aware, which is using the protobuf specification. Some things I already mentioned. So for example, the time to fuzz, it's way lower for coverage guided, since you just have to run it and find the corpus. But I will point the attention to the bolded text, which are actually the most interesting ones. So in the structure aware, I needed to write more than 20 versions of the harness, which is the code responsible for taking in the protobuf defined animated sticker and translating it to JSON, and then calling the right APIs in RLOT. While in coverage guided, I just needed to write it one time because it was always the same. The slowdown was also particularly bad. I think this is because I needed first to create an animated sticker from scratch, then translate it to JSON, and then test it against the potentially insecure RLOT APIs. Last but not least, the time to results is way longer, since it actually needed to run for way more time. You can see here it's per tree, in order to find the same issues or more. Because as we can see in the next slide, I have actually found 2 additional issues by using structure-aware fuzzing. And I think this is because mostly, as we have seen in the earlier slide, most of the mutated JSONs were broken JSONs, so they were useless, and they wasted so many CPU cycles. Another thing to note here is the coverage limit, because in coverage guided fuzzing, it heavily depends on corpus. So for example, if you didn't have a specific animation in your corpus, it's really difficult for the fuzzer to create it from scratch, since it will first need to stick to the JSON specification, and then also stick to the Lottie specification, and it's pretty impossible to do that. While in structure-aware, there is theoretically no coverage limit, since it should be 100%, but in this case, RLOT also included some APIs which were not used in the actual Telegram code, so you couldn't reach 100% because they were not used. Last point in this comparison is about the test case minimization comparison. So as we have said, both are slow in coverage guided fuzzing, since the animated sticker is pretty much a mess. Imagine like 3 kilobytes of JSON, one line JSON. While in structure-aware, it is scriptable, because it already knows what is the specification it needs to stick to. And it's also, the comparison is also direct, because it doesn't create meaningless animations part in the animated sticker. So let's move to the findings, then live demo and the exploit limitations. So as I mentioned earlier, I have identified 13 issues in total. This is the full list. We are going to have a look into the heap out of bounds right. But you can find all of the details on our website, shielder.it/advisories. Also note here that usually in this context, null pointer dereferences are useless, but in this specific Telegram chat context, it was a problem, since it will make the chat crash every time you open it, so you would not be able to recover the messages before the crashing animated sticker. So the non-tech-savvy people will not be able to recover the previous messages. They will need to either open the Telegram database and remove the animated sticker, or in some way instrument with Frida the phone. So let's have a look at the heap out of bounds right. As you can see here, there is a little preview snippet of the address sanitizer report. As you can see, there is also the stack trace below, and we can see that it actually starts in the render sync API, which, as we have seen in the quick start, it is used to render a specific frame number. You can see also that address sanitizer reports it as a heap buffer overflow, so it's a heap-based buffer overflow with a write of size 4 bytes. So this slide is a bit dense, so I will try to point with my mouse here the correct variable. So basically our input arrives at the stop, vgradient stops, and it will influence the start and cur variables. So in turn, it will also influence the cur color. And you can see that cur color is an unsigned int 32, which is of size 4 bytes. We arrive at the while loop, and you must note that here they don't check that pos is actually less than size, which is the color table array length. So potentially here we are able to write out of the color table bounds, which is what happens here. So let's try to do a live demo of this vulnerability. Okay. I will just try to reconnect it because it disconnected. Okay, I guess we can see the video I have prepared. Okay, so basically you can see on the right part of the screen my test device. Here I'm just showing the Telegram developers that I'm actually using the default settings for my device, and showing also my Telegram version, and you can see here that the autoplay is actually disabled. We can skip a little bit. Okay, here in the center part you can see the ADB shell on the actual victim device, and we are going to grab the logs for the actual crash in the Telegram app. In the left part of the screen, you can see that I'm gzipping the animated sticker because in Telegram they are actually used gzipped and not as plain JSONs. Then I will just send to my victim account the animated sticker, and we will see what happens now. So now it's trying to create the secret chat with the victim. Note also that the victim doesn't have the contact, the attacker contact imported in Telegram. And you can see that the victim automatically joined the secret chat without any interaction. Now the attacker is trying to upload the animated sticker to the victim chat, and you can see that we can control the text on the victim chat. Now you can see that it actually crashed, and here is the address sanitizer crash. Thanks. Okay, let's go back. So let's have some exploit considerations and limits. As I said, this attack is only possible in secret chats. This is because in my tests, I couldn't send malicious animated stickers in clear text chats, which are the default in Telegram. I think this is because Telegram is doing some kind of filtering on the server side, but I couldn't verify this also because the server-side Telegram code is not open source. So as we have seen, weak default settings, so for example, the autoplay feature and the documented server APIs allow a large-scale attack from a single computer because you don't need to have actually even a real device in order to attack anyone. The heap out-of-bounds write is only exploitable probably on 32-bit platform since it's a 4-byte out-of-bounds write. And last but not least, ASLR is still a big problem here because I couldn't find any remote info leak in order to bypass or a memory probing oracle like, for example, Saelo did in iMessage. So let's have some closing remarks to end this presentation. So how did they patch these issues? Of course, they patched the RLOT library, but they also introduced this defense in depth measure. As you can see, anytime the Telegram client receives an animated sticker, it will test if the received animated sticker is actually part of a public sticker set. So you cannot create animated stickers from scratch and send them to somebody. So they need to be part of a sticker set. So potentially you could also attack the Telegram server responsible for creating sticker sets, but as I said, the server-side code is not open source, so I couldn't verify this. Another potentially unrelated patch or new setting they introduced is the filter new chats from non-contacts, which is not enabled by default, but if enabled, it will automatically archive new chats from non-contacts. So you will not be vulnerable to clicking by error on a new secret chat created by the attacker. These are the patched releases. So as you can see, they are released almost 1 year ago, so you should all be patched now. And last but not least, an important dilemma, which is coming from quite some years, which is the competition between user experience and security. From my experience with this research, I've seen that Telegram strongly, for Telegram is very important the user experience and not the security, because as we have seen, they exposed a C++ library basically to the world. So you could actually exploit some victim by using these vulnerabilities. Thank you for listening to my talk. I will answer to any question you might have. Anyway, if you don't have any question now, I will be in the con, so you can catch up with me near here. Thank you.
It's a short talk, so we don't usually have time for questions, but I'm actually very curious. Do you find another tool, another app that you can use to keep fuzzing RLOT after the patches?
No, actually, after we sent 2 reports to Telegram because we fuzzed this for quite some months. After these defense in-depth measures, for example, the checking of the single sticker to be a part of a sticker set, after this patch, we stopped fuzzing because we would have to find an additional issue, which is a bypass for this patch, and then an issue in the RLOT library.
Yeah, because I figured there must be other apps that also use it, right? Not just Telegram.
Actually, the Samsung library for parsing LOT animation, so RLOT, for what I know, it's used by Telegram. Maybe some Galaxy Watch apps, but I didn't look into it.
So there's potentially a lot to find still.
Potentially, yes. But as I mentioned before, most of the Lottie vendors are actually using the Airbnb libraries, so Java and Swift library, which I didn't fuzz. They could have bugs, but I wanted to point the attention to the C++ code first.
Cool. Thank you. Thank you.
Thanks.
We're going to have a 15-minute break and then the next talk up. Thank you very much, Polict.
Thanks.